Ever imagine what it takes to track like every single Uber driver and rider, all across the globe every 30 seconds? It's a crazy amount of data. Today, we're diving into Uber, like right into their engine room to see how they handle that kind of fire hose of information.
It's an incredible scale problem, yeah.
Yeah.
And the fascinating thing is that their solutions, we can actually learn from them even if we're not running, some global ride-sharing empire.
For sure. We've got a great talk by Uber engineer Abhishek Verma. It's from Cassandra Summit 2016. Plus, we've got a breakdown of all that from high scalability to help guide our deep dive. By the end, you'll not just know how Uber manages literally millions of rides per second, but also why they picked the tools they did and what lessons we can all kind of take away from this.
Yeah, it's way bigger than just ride-sharing, right? It's like a window into the whole future of data management.
Okay, so let's unpack this. The first thing, we got to grasp the sheer size of this problem. Verma, he just throws out some mind-boggling numbers. Uber is aiming for 99.99% availability. That's like basically the always-on reliability that we're used to with, like, electricity.
Right. And to hit that level of uptime, especially for a service that's worldwide, forget about a single data center. It's just not going to happen. You need multiple data centers, not just for backup if one goes down, but to keep things fast, for users wherever they are.
Which leads us to their database, the one they chose, Cassandra. Verma gives a bunch of reasons why it fits Uber's needs perfectly. So first, horizontal scalability. You need to handle more data. No problem, just add nodes to the cluster. It's like adding more lanes to the highway.
Exactly. And it's made for fault tolerance. It's got these adjustable consistency levels. So you can fine-tune that balance between, okay, is every single piece of data perfectly in sync all the time? Or is there a tiny bit of potential lag, which you might accept to keep things running smoothly, even if a node drops? And, for Uber, even a few seconds down, that's lost rides. That's frustrated customers.
Verma even mentions their local data centers are hitting sub-millisecond response times, which is crazy fast. Plus, he highlights Cassandra's data model. It's really flexible. It lets them organize information in a way that makes sense for them. And it plays nice with other open source tools like Hadoop, Spark, all that good stuff.
Yeah, just those features alone, make Cassandra pretty darn appealing for any project with large data sets. We're talking way beyond just ride sharing here.
Oh, for sure. But here's where things get really interesting. Uber isn't just running Cassandra on a bunch of servers, right? They're using Mesos. It's like an operating system for their whole data center.
Think of Mesos as like the air traffic controller for your data center. Instead of individual servers, Mesos sees all the resources, the CPU, the memory, storage, all of it as one big pool that it can manage. It assigns these resources to different applications, keeps everything humming along smoothly and efficiently.
That is a great analogy. And Verma explains Mesos does this with a two-level scheduling system.
Mm-hmm.
So first, Mesos offers resources to frameworks, which are like these specialized applications, right?
Mm-hmm.
And then those frameworks handle scheduling their own specific tasks.
Right. And Uber, well, they took this a step further, which is classic Uber. They actually teamed up with Mesosphere to build a custom framework. It's specifically for running Cassandra on Mesos. They call it Ducos Cassandra Service.
Now, I know what you're thinking.
Yeah.
Why not just run Cassandra straight on the servers? Why all this, extra stuff? Well, Verma actually addressed that directly. Uber has a ton of different Cassandra clusters. Each one has its own purpose. They need to be sure that if one cluster has a problem, the whole system doesn't go down.
Right, exactly. Think about it like separate compartments in a ship. One gets flooded, but the others, they stay afloat. Uber, they really prioritize this kind of isolation, this flexibility over, squeezing out that last tiny bit of performance. And surprisingly, the performance hit from running Cassandra in containers is only like 5 to 10%, according to the high scalability article.
That's a pretty small price to pay for all that extra control, right?
Yeah, absolutely. It's a trade-off, but it makes perfect sense for what they need.
So they've got Cassandra running great on Mesos, but Uber didn't stop there. They've got some pretty clever tricks to optimize things even more.
For example, they use this thing called node-by-node repairs. It's on primary key ranges. This way, they can synchronize data across the cluster without slowing things down performance-wise. And when they add a new node, they don't just delete all the data from the old one right away. They have this whole separate process to clean things up, but in a really efficient way.
So it's not just about adding new data, but making sure the old stuff is cleared out right, which is smart.
Exactly. And to make sure that their data is always there, even if, like, a whole data center goes offline, they've got this multi-data center replication strategy going on. Yep. They'll periodically sync the seed nodes, the ones that help new nodes join the cluster, across all their data centers. This lets Cassandra's gossip protocol, that's how the nodes talk to each other, share information about the cluster's structure, across different locations.
It's like they thought of everything. So we've covered how they set things up. But how does this all perform in the real world? What kind of numbers are we talking about?
Well, are you ready for some impressive production metrics?
Always. Hit me with those numbers. What kind of performance are they actually seeing with this whole setup?
Okay, so as of 2016, right, Uber's system had about 20 Cassandra clusters. They were spread across data centers, both on the east and west coasts of the U.S.
Okay.
They actually used to have 2 more in China, but they shut those down, after the merger with Didi.
Right.
But all in all, these clusters were running on roughly 300 machines.
300 machines? That honestly doesn't seem like that much, considering the mountain of data they're dealing with.
That's the crazy part. The numbers get really wild when you look at the throughput. Their 2 biggest clusters, they were handling over 1 million writes per second.
Wow.
And something like 100,000 reads per second.
That's incredible.
Remember, one of these clusters, it's responsible for storing all those location updates from riders and drivers, coming in every 30 seconds.
Yeah, that's a mind-blowing amount of data to keep track of, for sure. What about latency, though? Are they sacrificing speed to achieve that kind of crazy scale?
Nope, not at all. They've actually managed to get a mean read latency of about 13 milliseconds.
Okay.
And a write latency of just 25 milliseconds.
Wow, that's fast.
And get this, they're using the local quorum consistency level mainly.
So
that means they're not giving up data accuracy for speed.
So they've got strong consistency, high throughput, and low latency. It's like they've achieved the holy grail of database performance.
Yeah, it really is some impressive engineering. But it's key to remember, Cassandra isn't their only tool, in their data storage toolbox.
Wait, they have even more up their sleeve. Tell me everything. What else are they using?
So they've also got this in-house solution they developed. It's called Schemeless.
Okay.
It's like a sharded MySQL store.
Interesting.
And their long-term plan, is to use both Schemeless and Cassandra as their primary storage options.
So it's kind of like a two-pronged approach.
Mm-hmm.
Cassandra for all that real-time, high-volume data, like location tracking, and Schemeless for everything else.
Yeah, that seems to be the strategy. They also mentioned they had some existing React installations. They were planning to migrate those over to Cassandra as well.
Oh, interesting. So we've gone pretty deep here talking about distributed databases, container orchestration, multi-data center replication. We even talked about a custom-built framework. What does it all mean, though, for the average person? What's the main takeaway for someone who's not running, a global tech company?
I think the most important thing here is that even these huge data challenges, right, they can be solved with a mix of smart engineering, open source tools, and some creative solutions. Uber's system is a perfect example. It shows what's possible when you embrace automation, treat infrastructure as code, to manage these complex distributed systems.
It's actually fascinating to me how much of what Uber built relies on open source technology, like Cassandra and Mesos. It really shows the power of the open source community to tackle real world problems.
Oh, absolutely. And this approach means that companies of all sizes can benefit from these advances. You don't need, Uber's crazy resources to use the principles of containerization, resource management, and distributed data stores.
So it's really about applying these concepts to your own projects, right? Even if they're on a much smaller scale.
Exactly. This whole deep dive, it wasn't just about Uber. It was about what data management will look like, going forward, and how we can learn from those who are pushing the boundaries.
Yeah, it really makes you think. We always hear about these massive systems, right, built by these huge tech companies, and it's easy to just assume they're not relevant to us, to our own work. But Uber's whole journey with Cassandra and Mesos, it shows that the ideas behind it all, they're surprisingly applicable, even at a smaller scale.
And what's really cool is that Uber isn't just using these technologies, they're contributing to them too. Remember that custom framework we talked about?
Yeah.
The Duckus Cassandra service. That's actually an open source project. They developed it with Mesosphere collaboratively.
So they're not just they're giving back to the community. That's awesome.
Yeah, it really highlights a key point from this deep dive. Innovation in data management, it's not limited to big companies.
Yeah.
Open source tools and sharing knowledge, it empowers developers everywhere to build systems that are robust, scalable, all of that.
So zooming out a bit here, We've seen how Uber manages 1 million writes per second. What does this even mean for the future? Where's this all heading?
Yeah, that's the real question, isn't it? I mean, as data just keeps growing and growing, will architectures like this become the norm? Even for, smaller companies, will we all have to be experts in distributed systems and container orchestration just to keep up?
Right. And what about the tools themselves? Will it be Cassandra? Will it be Mesos? Will those stay the go-to solutions? Or, will we see something new come along? It really feels like we're only starting to understand what's possible.
That's what makes this whole area so exciting. I mean, this deep dive, it gave us a peek into like the leading edge of data management, but it also raises more questions than it answers. There's always more to learn, more to explore, more to build.
Totally. So wrapping things up, we did a deep dive into Uber's data infrastructure. We talked about how they use Cassandra, Mesos, even that custom framework they built. We saw how they handle these massive amounts of data, while keeping things available and keeping latency low.
And even more importantly, we found some principles that apply way beyond ride sharing, right? This deep dive, it's a reminder that the future of data management, it's distributed, it's scalable, and it's surprisingly accessible, for anyone who's willing to learn and experiment.
Absolutely. So we'll leave you with this. What data challenges are you facing, and how could the tools and techniques we discussed today help you, solve them?
Keep learning, keep exploring, keep building. Until next time.